All right, my lovely students. So now we're going to take a look at section 2.2. This is the start of the unit circle. So we talked about angles in 2.1 and arc length, radian measure. Now we're going to start looking at trig functions. The big thing to know about trig functions is trig functions take an angle and produce a ratio of sides of a triangle, which we can use to figure out the lengths of the sides of triangles. So they give us a way to relate angle measure to distance or length. So our two functions, sine and cosine, are going to correspond to the x and y distance of a point on the unit circle that's associated with the angle on the unit circle. All right, so that's how the book defines it, x and y. Yeah. So you can see it in the picture here a little bit better. So a unit circle has a center at 0, 0 and a radius of 1. So it's a unit circle because the radius is 1 unit. Because it's a unit circle, the length of the intercepted arc is equal to the radian measure of the angle. Because S equals R theta, if R is 1, then the arc length equals theta, as long as it's in radians. So that endpoint on the unit circle becomes the cosine and the sine. So specifically of the angle that we're drawing in the unit circle here. Now, another way to see this, and the way that my brain tends to focus on here, is that right here, that is a right angle. So we have our angle T here. So with a right triangle, we have an adjacent side and an opposite side, as well as the hypotenuse. Ooh. So I will post another video that really digs into the whole naming of the sides and where the trig functions come from that. But I just want to put it up here. If that's something that's familiar, then seeing these triangles embedded in the unit circle may make more sense. I am going to emphasize them because I find in later questions, understanding this here will help with future stuff. All right, but the book just straight up says the x distance is cosine, the y distance is sine, and that's coming from sine is opposite over hypotenuse. The hypotenuse is 1, so the sine of t is the measure of the opposite side in the unit circle. The cosine of t is the measure of the adjacent side. So if you have that SOHCAHTOA association, this is following that. All right, a little bit of notation notes here. Mathematicians are lazy. So instead of saying the sine of t and the cosine of t with the parentheses, we got lazy. So you're going to see sine, and then the t will be italicized, and cosine, COS, and the t will be italicized. So it almost looks like cost, but not quite. So after a while, you get used to reading it, but initially, just whenever you see SIN or COS, you want to knee-jerk reaction to wait, trig functions, not cost. We are also going to look at squares, like sine squared and cosine squared. And if you look at what the notation means, 2 sets of parentheses and then the squared, that's a lot of parentheses. So we put the squared on the sine. This is to distinguish it from if we were squaring what's inside the function. So these are not equal to like this, the sine of t squared, where the t squared is completely in the input. That we have to write like that. We have to put the parentheses around it. Now, the other thing behind going over this notation is that if you put sine squared, your calculator will not understand what you're trying to say. But most of what we're going to do, we shouldn't be using a calculator for that. So we'll be all right. All right, so our try it number 1 here. A certain angle t corresponds to this point on the unit circle, and they labeled the radius of 1. And then they want us to find the cosine and sine of t. So, let me grab a different color. All right. So if I draw in the x and y distance, that makes a right triangle. It is negative square root of 2 over 2 units to the left, and then positive square root of 2 over 2 units up. So our angle on the unit circle is this, but inside here, we're going to have what's called a reference angle. The adjacent side to the reference angle is our cosine. So that's our A in SOHCAHTOA. So the cosine of this t is negative square root of 2 over 2. So we will get negative results. And what that's going to mean in some applications is it's a designation of direction. So forward positive, backwards negative. Just depends on the context of the problem, but don't automatically assume negative numbers must be wrong. They can have meaning. And then our sine of t for this triangle is that vertical distance, the measure of the opposite side, which is the positive square root of 2 over 2. So the lengths of those sides, when we say the length of something, length is actually typically an absolute value. So the lengths are equal. The side of the triangle itself, though, has a negative in it because the point on the unit circle is in quadrant 2. All right, we got a whole bunch of information that all kind of like cross-references and gets all together. So just bear with me. I'm going to try to make the connections as we go. All right, so looking at the unit circle, anywhere I stop, there's a sine and a cosine value for that point, and there's an angle associated with that point. And that includes our cardinal directions, the very top, the very left, the very bottom, the very right. So our top one up here, the XY coordinates are 0, 1. So remember, I'll sometimes, like when I do these in my head, I'm kind of like thinking, all right, I go to that one. So there's my X, there's my Y. And then I see my X is the adjacent side. So I'll remember that everything in the unit circle is cosine for the X coordinate and sine for the Y coordinate. So following that pattern then, for this angle, which is 90 degrees or pi over 2 radians, the cosine of 90 degrees is going to be defined to be 0, and the sine of 90 degrees is going to be defined to be 1. Now, same song, second verse. Let's get out here to 180. The coordinates of this point, so this is superimposed on an x and a y axis, and we know the radius is 1 unit. So this is going out to -1 on the x-axis and 0 on the y-axis. So the cosine of 180 degrees is -1, and the sine of 180 degrees is 0. All right, then our third one way down here is 390s, 270. This is 0, comma, -1. So the cosine of 270 will be 0, and the sine of 270 will be -1. Gonna move that up there real quick. So the one we didn't cover here is, it's kind of silly, but 0 degrees, that is a point on the unit circle. That's the point on the right. We kind of consider that our starting point, but it is a point. So there is a cosine and a sine measure for that. So 0 degrees and 0 radians are the same thing. They're this right here on the axis. The initial and terminal side of the angle are the same thing. And the ordered pair of that is 1, 0. So the cosine is 1 and the sine is 0. Now, if I did a full circle, I get back where I'm started, but that angle measure, if you will, is 360 degrees. And it's going to be the same as 0 degrees. So we can see here the cosine goes 1, 0, -1, 0, 1. The sine goes 0, 1, 0, -1, 0. So like those 5 points are going to give us the rough outline of the graph. And those are actually like as big and as small as it can get. That gives us the highs and the lows and the middle number. Okay. Pythagorean identities. So remember how I said when we plot that point on the unit circle, there's always a triangle we can draw? So we'll just drop an arc there. Call that angle T. Then our x distance here is the cosine of t. The y distance is the sine of t. And the hypotenuse, because it's a unit circle, is forcibly defined to be 1. So our Pythagorean theorem tells us for any triangle, with side lengths labeled like so, or you can flip the A and the B, but C is always the hypotenuse, always opposite the 90-degree angle. For any right triangle, A squared plus B squared must equal C squared. So if we apply that to our trig triangle in the unit circle over here, we're going to get cosine squared t plus sine squared of t equals 1. So as long as the t's are the same here, so it's not cosine squared of alpha plus sine squared of beta, the angle measures must be the same. Most problems we look at, they will be the same, so you kind of get used to this assumption of, oh yeah, cosine squared plus sine squared is 1. I just bring it up early on, like there's this underlying assumption that you'll tend to make that it's always about the same angle, and that works just fine until we finally give you a problem where it's not. So I'd rather be deliberate about it now. But that is where our Pythagorean identity comes from. And we can actually make use of the Pythagorean theorem here to answer more questions about trig functions in the unit circle. All right, so our trait number 3 here tells us if the cosine of an angle is 24 over 25 and t is in the 4th quadrant, find the sine of t. All right, so if t is in the 4th quadrant, now remember our quadrant numbers. We start up here with quadrant 1, and then it goes counterclockwise. So 2, 3, and 4. So if t is in quadrant 4, and then it can even help to like, there's t. So let me talk through what the book would have you do here. So for this point here, if the cosine is 24/25, then that is telling us that the x distance is 24/25. And we're wanting to know what is the y distance. So that's two sides of a right triangle. The third side is 1. And then we can use the Pythagorean theorem to solve here. So 24/25 squared plus y squared equals 1 squared. Now, if you're like me and you don't like dealing with fractions, algebraically, what you can do is multiply by the denominator. So when we square a fraction, we square the top and square the bottom. So what I'm going to do to clear the fraction is multiply everything by 25 squared. So now here I have 24 squared. Here I have 25 squared y squared. And over here I'll have just 25 squared. And then we can just keep solving like that with the y in there. It gets a little ugly, but it'll work. All right, so we minus the 24 squared. So 25 squared is 625. 24 squared is, I want to say 589, but I'm just going to cheat and, no, 576. All right, so we have 625 minus 576 is 49. Well, I know 49, that's 7 squared. So I'm going to divide by the 625. So if y squared equals 49 over 625, and now we would square root, and because we are choosing to square root, we must consider the plus or minus. Sorry about this, a little snafu. All right, that should be okay now. We'll just continue over here. So we have y could be the positive or the negative. Square root of 49 is 7. Square root of 625 is that 25 that we started with earlier. So the length of the y segment is 7/25, but let's go back and look at that initial picture. That y is going down. That point in quadrant 4 will have a negative y value. So the x value is 24/25, but the associated y value would be negative 7/25, which means our sign is negative 7/25. But if I had a triangle in quadrant 1, I would go through all of that same work, but I would choose the positive square root because the triangle is in quadrant 1. So what you're going to see on a lot of these questions is, in order to fully determine the other trig functions, you need two pieces of information. One of them is what one of the trig functions equals, and then the other is some way to know what quadrant it's in. There's a few special angles, the extremes, 1 and -1. If I know cosine equals that, there's only one spot cosine is +1. There's only one spot cosine is -1. Everything else, though, there's multiple places, so we have to place the function. All right. So the unit circle has specific values picked off, and these values are coming from our special right triangles. So hopefully these are vaguely familiar from your time in calculus or in geometry way back when. So one that we saw a lot of was the 45, 45, 90 triangle. And this triangle, the two legs are both equal measure, and then the hypotenuse is equal to the square root of 2 times that measure. The other triangle we deal with a lot is the 30, 60, 90, and that's because the side opposite the smallest angle is 1 unit, and the side opposite the largest angle is 2 units. So we have a 1-to-2 ratio of sides there, and then the Pythagorean theorem tells us the third side is the square root of 3. But these triangles are bigger than the triangles in the unit circle, because the unit circle has a forced radius of 1. So what we're going to do is, for the 30, 60, 90, well, my pictures are backwards, but I divided all the sides by 2. So 2 over 2 is 1, 1 over 2 is a half, square root of 3 over 2 we leave as square root of 3 over 2. So when I'm looking at my 30-degree angle here, I see to go from the starting corner to the finishing corner, I move horizontally square root of 3 over 2. I move vertically 1/2. So my cosine of 30 and my sine of 30 are going to be square root of 3 over 2 and 1/2 respectively. And that's what we have here. Sine of 30 is 1/2, cosine of 30 is square root of 3 over 2. Now we could, from those two pieces, figure out the tangent, cotangent, secant, and cosecant. We're going to do that in 2.3 though, so I'm going to hold off on that part. But before we divided everything by 2, if I go back up here, the sine of 30 degrees is the opposite side measure over the hypotenuse measure, 1 over 2. Sine of 30 degrees is 1/2 in this larger triangle, and it's 1/2 in this smaller triangle. So the size of the triangle does not impact the trig values, only the size of the angle. So that is something that we make a lot of use of, especially in applied situations. Now, our crazy triangle here that had the square root of 2 as the radius, well, we would divide everything by the square root of 2 to get a similar but smaller triangle. Dividing 1 by the square root of 2, though, looks ugly. So we have this process called rationalizing so that the square root is on top of the fraction. And the only reason we rationalize is from back in the day before calculators, when students used slide rules. It was easier to take an ugly decimal like square root of 2 and divide it by 2, but taking an ugly decimal of the square root of 2 and dividing it into 1 was a giant pain. When the ugly decimal is what you're dividing into, you divide until you have the number of decimal places you want for accuracy. The other way around does not work if you're doing it by hand. All right. But our 45, 45, 90, this shows us that 45 degrees, the cosine is square root of 2 over 2, and the sine is square root of 2 over 2. So we now have the cosine and sine of our 30 degrees and our 45 degrees. And if we go back to this one and I flip it, so I have my 60 degrees. Across from 60, the longer leg is square root of 3 over 2. The shortest leg across from the smallest angle is 1/2, and our radius is still 1. So I just took my triangle there and flipped it so that my 60 is in the standard position for an angle. So if I put the origin there, now that point is on the unit circle, and that's my cosine of 60 and my sine of 60. All right, so I got sine and cosine for all the important angles in the unit circle between 0 and 90 degrees. So with those two triangles, we can actually fill out the unit circle, this first quadrant. This is the piece of information I recommend putting on flashcards and memorizing. You want to be able to pretty quickly be able to say that the cosine of pi over 6 is square root of 3 over 2. And you need to be able to remember that pi over 6 is 30 degrees, pi over 3 is 60, pi over 4 is 45. A relatively fast way to get the other angles, but we are going to give you a unit circle on the test. You have to remember that cosine's the x, sine's the y's, but you're not going to have to regurgitate the whole unit circle on something. All right, I'm going to pause it here and then we'll fill out that quadrant at the start of the next video.